Okay, hi everyone. Hi again. So in this part of the video, I'm going to talk about the last part of the theoretical process of Bode plots. So I'm going to talk about the simple pole and simple zero, which were one of the factors that we have in in the transfer function. Okay, and then as I said before, I'm not going to go through all the process on how to draw the quadratic pole or zero, which are the higher orders, because you will not see them in this course, or if you see them, it's just in a way that you can use the table to draw them, and the process is a little complex, so it may cause some confusions for you. But if any of you is interested in knowing how we have that plots for the quadratic pole or zero in the book, you can come to my office hour and we can talk about it. So as I said, now I will finish this process of Bode plot, drawing the Bode plot, and then in the next video that hopefully I'm gonna upload it on Sunday, I will do one example, or hopefully a couple of examples about how to draw a Bode plot, so different transfer functions, and then I'm going to draw them. And please watch them before the Tuesday lecture. So on Tuesday, I will see if you still have problems about these parts that I just talked in the video. I'm going to go over all of this material again. If not, we'll do more examples about Bode plots, and then you can get more familiar and more comfortable with it. So let's go ahead and start with the simple pole and zero. Okay, so the third factor that we may or may not have in the transfer function is either a simple zero or even both of them. So a simple zero, which is 1 plus j omega over z1, or a simple pole, which is 1 over 1 plus j omega over p1. And as you can see, in all of these parts that I just talked about, and specifically in this one, which is a polynomial, you can see that this one is 1, right? And before I said that in the polynomials of drawing the Bode plot, you should have this factor equal to 1 here, correct? Okay, so let's go back there. So one thing that I want to point to it before starting talking about simple pole and zero is why we do not start the frequency axis from 0. So basically, if I have 20 log base 10 of omega, okay, so now I want to find the magnitude of this value, okay, in decibels. So I said that I'm not starting from 0. Why? Because if I set omega equal to 0, the magnitude will be 20 log base 10 of 0. So what is this? We know that if I want to solve this, so 10 to the power of something should be equal to 0. How can 10 to the power of something be equal to 0? So for sure, this should be 1 over 10 to the power of infinity equal to 0, correct? So 10 to the power of negative infinity is equal to 0, okay? So this value is negative infinity. So when frequency is equal to 0 in the semi-log plots, in the frequency plot, it is in negative, far away negative infinity. That's why we are starting from very small omega, and typically we are setting that small omega as 0.1, okay? So this was one thing that I want to point out here. So let's go back to what we were talking about. So the simple zero, 1 plus j omega over z1. All right, let's go and find the magnitude. So the magnitude in decibel of this value is equal to 20 log base 10 of the magnitude of 1 plus j omega over z1. This is the magnitude. Okay, so for small frequencies, okay, we want to see what is this value for small frequencies. So basically for small frequencies that are omega approximately equal to 0, so this means small frequencies, okay, we're going to get a magnitude of 0. And for large frequencies, which is when omega goes to infinity, so these are very large frequencies, we're going to have 20 log 10 of magnitude. So here I'm setting omega equal to infinity. Okay, so this means that it has two factors, right? So this is going to infinity, so it will be much higher than 1. So I will neglect 1 here, and then the magnitude here is omega over z1, right? So this is when omega is large. Okay, now let's see what is in between, what is happening in between. So first we have 0, then we have infinity. So we should have some break frequency, right? A frequency in which the plot is increasing from 0 to infinity. Okay, so let's see what is that. So we can say that z1, which is our 0, is the breaking or corner frequency. Which is, in this example, it is 20 log 10 of 1 plus j, which is 20 log base 10 of square root of 2, and this is approximately equal to 3 decibels. Okay, so now let's go ahead and draw this Bode plot as we have here. I mean, with the values that I already found. So this is omega, this is my h, so basically this is our h. This is one of the factors that we have in h, right? A simple 0. So we said that we start from 0.1, okay, and then we go somewhere here, which is our 0, okay, and then we have the infinity. Alright, so let me change the color. So it will be 0 for small frequencies until some z1, and then at z1 we said that it is 3 decibels. Okay, so let's say here we have this 3 decibel. So let me just erase this for a second, and then I erase everything. So we know that it is increasing from 3, and then it reaches to 3 decibels at z1, and then it goes to infinity. So if you want to draw it just approximately, it goes and reach 3 decibels in z1, and then it goes to infinity. Okay, but the Bode plots that we are using in this course are approximations of the actual Bode plot that we have. What does that mean? So this is 3 decibels. So we said that the Bode plots that we are drawing here in this class, they are the approximations of the actual Bode plot. So if we put a transfer function in MATLAB and then ask MATLAB to draw the Bode plot for us, it will show you something like this. So the plots will have some curves. Okay, so I'm going to do one of these examples in front of you in MATLAB in class so you can see what I mean. But in the class we will go ahead and do some approximations. So we say that, okay, this is 0, and then we will consider this 3 decibel as a small value, a magnitude, okay, small magnitude, and then we say that it goes up. Okay, so basically this is the approximate plot, the black one, and then the pink one is the actual plot. Okay, so now we want to see what is the slope that this Bode plot is increasing, okay, with. Let's see what is that. So we have in z1 we say that approximately the magnitude is near 0, okay, And let's say, for example, if omega is equal to 10z1. Okay, let's see what will we have there. So you remember that I said when I was talking about the decade, I said that in the frequency plot, in the frequency axis, we're increasing with a ratio of 10. Okay, so basically I'm saying that this is 10z1. So what is the magnitude here in decibels? We're going to have 20 log 10 of 1 plus j 10 z1 over z1, right? And then this is equal to 20 log 10 of, so this magnitude here is square root of 101, which is approximately equal to 20 log 10 of 10. Okay, so I said that this 101, the square root of it is near 10, so we can just consider it as 10, and this is equal to 20, right? So we know that at 10z1 we have to reach the magnitude of 20 decibels, 20 dB. So we can see that here we have 0, here we have 20, correct? And then here is 1 decade, correct? So we can say that this waveform is increasing with the slope of 20 dB per decade. All right, so this was for simple 0. Okay, and as you can see in the table 14.3, right, it was table okay, I don't know where I wrote that, but anyway, oh, here it is. It is table 14.3. You can see that we have the waveform of simple 0 as this one. Okay, so it is 0 until it reaches the 0. Okay, so until it reaches the 0 of that specific term, and then it increases with 20 dB per decade, and that depends, this 20 dB per decade basically is 20 n dB per decade, in which that n is the power of this simple 0 or our simple pole. Okay, now let's see what is what does the phase plot looks like. So let me go here. Let's draw the phase plot for simple 0. Okay, so our transfer function, so we just assume that we have this one term, is 1 plus j omega over z1. Okay, what is the phase here? Is tangent inverse of omega over z1. All right, so let's see what are these phase, so how I can draw the phase plot of Bode plot. So again, we go here for small values of omega, so basically approximately equal to 0, we're going to have tangent inverse of 0, which is 0. When omega goes to infinity, we are going to have a 90 degrees, right? And when omega is equal to the breaking or corner frequency, we're going to have tangent inverse of 1, which is 45 degrees. Okay? And let's see until when these small values of omega gives us the plot as 0. So let's say that, for example, if we have omega equal to 0.1 z1, so we're going to have phi equal to tangent inverse of 0.1 z1 over z1, correct? This is equal to tangent inverse of 0.1. Okay, so this is increasing, right? Tangent inverse of 0.1 is bigger than 0, correct? So it says that when omega goes is equal to 0.1 z1, the plot starts increasing. Okay, these are all approximations that we are making in order to have the plots that are in table 14.3. Okay, so the plot will be like this. This is omega. This is the phase this time. So we are gonna have some z over 10, z1 over 10, and then we're gonna have our breaking frequency, and then we have 10 z1. So basically for 10 z1, okay, we are increasing per decade, right? For 10 z1, let's see what is phi. Phi is equal to tangent inverse of 10 z1 over z1, okay, which is tangent inverse of 10, and tangent inverse of 10 is approximately 84. Basically it is 84 degrees, but since we know that when we have a larger omegas, okay, we're going to have 90 degrees, we will consider this as 90. So I will show you how the actual plot and the approximate plot will look like. So we say that at z over 10, okay, so it is 0 until z over 10. Okay, and then we go up. Not very good. I didn't draw it really good. And then we will be here. So in 10 z over 1, we say that it is 84 degrees, and then it goes to 90. Okay, so basically it has some curves here, right? But the plot that we are looking for, so the approximate plots of the Bode plot, is that before z over 10, we have everything equal to 0. Oh, let me draw it with black so you can distinguish it. It's equal to 0. Okay, we're saying that at z1, we are having 45 degrees. Okay, and let me just make this axis a little bigger. And then at 10z1, we are make this approximation. We say that it is going to 90. Okay, so for larger omegas. So that's why the plot that we are looking for in this class is equal to this. And basically, so this pink one should be here. It is 84, right? It is less than. So it is something like this. Okay, I'm going to draw this for you in MATLAB so you can see what I meant. But the waveform that we are looking for is the black one. Okay, so it is 0 until we reach z over 10, and then it goes up. In the middle point, it will reach 45 degrees, then it goes up, and then it will be 90. And as you can see in the table, we have this as 90n, which was the power here. Okay, so if I want to find what is the slope of this waveform, what is the slope of this sketch, see here, we see that here we have 1 decade, right? And in this 1 decade, how much does the phase change? It changed 45 degrees. So we can say that our slope here is 45 degrees per decade. All right, so this was for the 0, and then the pole, it is going to negative 90. So it goes 0 until p over 10, and then it goes down to minus 45 at p1, and then at 10 p1, it goes to negative 90, negative 90n. Okay, so this was for the simple pole and 0. And as I said, I'm not going to talk about this process for quadratic pole because you'll be confused, completely confused about this process. But if any of you is interested to know how, you can come to my office hour and we can talk about it. Okay, because these processes are not necessary for sketching the Bode plots. Basically, they are necessary, but since you have the table, you can use the table and then draw the Bode plots. Okay, it's good to know all of these. So I hope that you all understood what I just talked about. On Tuesday, I'm going to ask you again and see if you still are confused about Bode plots. For sure, I will go through all of these material again. So I have all these notes. We can go through them in class as well. So tomorrow, which is Sunday, I will upload a video, hopefully with a couple of examples about Bode plots, so you can see how we can draw the Bode plot and how we can add the graphs, add the plots graphically in order to have our Bode plots. Okay, I hope everyone understood these lectures. So thank you.